All right, we are finally going to get to do some calculus in your calculus class today. We're going to talk about taking derivatives when it comes to parametrically defined curves. So you might remember this one from when we had our introduction to parametrically defined curves a while back. And let's say that we wanted to find the equation of a tangent line to this curve somewhere, or if we were thinking of this as like the flight path of that bird going through the air, maybe we wanted to find the velocity that the bird was going at a particular moment on the path. For either of those things, we would need to be able to take a derivative. And the trouble with this is that all of our derivative rules require y to be a function of x, all of our product rule, chain rule, all of those things. And clearly y is not a function of x here. This thing does not pass the vertical line test. So we're going to do a little bit of a cheat. Okay, so let's just focus in on some point here, maybe like x equals 3. And obviously there's 2 points where x is equal to 3, one on top and one on bottom. I'm going to focus in on the spot on top. Okay, so let's say we want to find the tangent line to that curve, or the velocity of the bird, whenever x is equal to 3. When I zoom in like that, we could reasonably believe that y was a function of x, right? Just in this small window, it looks like there could be some function that would represent this curve where x is equal to 3. And really, when you're talking about the tangent line, we only care about what's going on at x equals 3. We don't care about the rest of the curve. All right, so we're going to kind of think about the derivative in terms of what if there was this mysterious function, I don't know what it is, but what if it existed and I could take the derivative of it? All right, so in the box, I have the parametric equations for the curve that we were just looking at. X is equal to some cubic function of t, y is equal to a quadratic function of t. And remember that t is that third variable that's behind the scenes telling x and y what to do. So we said, though, maybe if I pick my spot and I zoom in on the graph, there's this mysterious function out there where I could think of y as a function of x. Okay, but I don't know what that function is, so I can't just go take its derivative somehow. But what I would really like to find, I want to find f prime of x. That's really what I want. All right, but how am I going to do that? Okay, everything I know about x and y is in terms of t, so really the only variable that I can take the derivative with respect to is t. So I'm going to do this odd-looking thing. I'm going to take the derivative with respect to t. I've got so many variables going on right now that this Leibniz notation is going to help us keep track of what's going on. So I'm going to take the derivative with respect to t of y, all right? And that would not be hard to do, right? I can look at y and its derivative is going to be 2t minus 2, okay? So we're taking the derivative with respect to t of y, and then I'm also going to take the derivative with respect to t of this mysterious f of x function on the right. And remember, I don't know what this function is, so I don't actually know how to take its derivative. All right, so we're just going to kind of do this in theory. All right, so when I take the derivative of y with respect to t, I'm going to get dy dt. And I'm going to leave that general because we want this to be a formula that would work for all parametric curves, not just the one that I've got up there in the box. All right, so I would get dy dt, so the derivative of the y equation, whatever that happens to be. And now I'm going to take the derivative with respect to t of something written as f of x. All right, so the thing inside the box on the right-hand side of the equation, we're actually going to need a chain rule over here. All right, because we've got this f of x, which is going to be our outside function. And I've got x in the parentheses. Remember, x is equal to a function of t as well, right? It's t cubed minus other bunch of stuff. All right, so we're going to treat that like the inside function. All right, so let's remember how to take the chain rule. We take the derivative of the outside function, leaving the inside function alone. So the outside function is the f. I'm going to take the derivative of the outside function, leave the inside function alone, that x, whatever the formula is for x, and then you multiply by the derivative of the inside function. So the derivative of the inside function is going to be the derivative of x with respect to t. All right, so that f prime of x there, that's the thing I wanted in the first place, right? So I can take both sides of this equation and divide it by that dx dt. It's starting to look like a mess on the left, but it's all right. We're going to make it work out. All right, and that cancels out that dx dt, and now I've got that f prime of x, and that's really what I wanted. F prime of x is equal to dy dt on top and dx dt on bottom. All right, So it just says take the derivative of the y equation with respect to t. That's going to be easy to do, 2t minus 2. Take the derivative of the x equation down on the bottom of that fraction with respect to t. It's just a polynomial, that x cubed, the t cubed equation. All right, and divide those two. That's going to give you a formula for f prime of x, that mystery function that we don't know what it is. All right, so in this formula, we usually don't write f prime of x. We're going to stick with this Leibniz notation. We're actually going to write this as dy dx. Remember, that was our Leibniz notation for derivatives in Calc 1. All right. So that's going to be our formula for finding the derivative of a parametrically defined curve. And it almost makes sense that dy dx would be equal to this complex fraction on the right. If you want to take a second to do like a dividing fractions, like a keep change flip, it even kind of looks like the dt's would cancel out and give you dy dx. All right, so in the next video, we're going to do a couple of examples using this formula.